Vector addition and scalar multiplication share many of the properties of ordinary arithmetic. Properties of vector addition and scalar multiplication. Let u, v, and w be vectors and let c and d be scalars, and the properties listed below are true. So I hope you see that u plus v is the same as v plus u. And then if you have u plus a negative u, that equals 0, and so forth. Now, the only one that we're going to focus on right now that we need is number 9. So when you have a constant times the vector and a magnitude, we're just going to take that constant out with the absolute value with it, so it'll always be positive, and then multiply it to the magnitude. So let's try that. Find the magnitude of a scalar multiple. Let u equal 1, 3, and v equal negative 2, 5. Find the magnitude of each scalar multiple. So how you do this is we take the 2, right, the absolute value of that, and then we find the magnitude of u. Now remember, the magnitude is just the square root of v1 squared plus v2 squared. So it's actually pretty fast. So this is going to be the absolute value of 2 square root of 1 squared plus 3 squared, which is the absolute value of 2 times 1 plus 9, or 2 square root of 10. Okay, so to find the magnitude of negative 5u, what we'll do is we'll take out the negative 5, then absolute value, and then the magnitude of u. So that's going to be negative 5 times the square root of 1 squared plus 3 squared. It's the same as before. And so the negative 5 becomes a positive 5 square root of 10. Then letter C, so 3, and then the magnitude of v, that is going to be 3 times the square root of negative 2 squared plus 5 squared. So that is 3 square root of 4 plus 25, or 3 square root of 29. So try the 3 examples here. So doing this, you should have gotten 3 root 17, 2 root 13, and 5 root 13. So now we want to find a unit vector. So let's take a look at some information first. In many applications of vectors, it is useful to find a vector that has the same direction as a given non-zero vector v. To do this, we're going to divide the vector v by its magnitude to obtain this formula. So this is important to write. You want this information here. So you take v, divide it by the magnitude, and then we're going to pull the v out to the side, and then we'll actually distribute it back in. So note that u is a scalar multiple of v. The vector u has a magnitude of 1 and the same direction as v. The vector u is called a unit vector in the direction of v. So let's try it out. Finding a unit vector. So we're going to find the unit vector u in the direction of v equals negative 2, 5, and verify that the magnitude of u is 1. So what we do is we're going to take u equals a vector over the magnitude of that vector. So the vector is negative 2, 5 over the magnitude. And remember, the magnitude is just this and this squared. You add them together. So negative 2 squared plus 5 squared. So this is going to be, we rewrite it as 1 over the square root of 4 plus 25 times negative 2, 5. And so this is going to be 1 over square root of 29 times negative 2, 5. Then the vector will be, and you distribute it, negative 2 over root 29, and then 5 over root 29. Of course, you should rationalize the denominator. So negative 2 root 29 over 29, and 5 root 29 over 29. Now, to verify that the magnitude is 1, what we're going to do is we just take this and then square it. So we're using basically the magnitude again. So you're doing this, and then you're taking I'm going to use the one without a rationalized denominator. Negative 2 over root 29 squared plus 5 over root 29 squared. So this is going to be the square root of 4 over 29 plus 25 over 29. So this is the square root of 29 over 29, which is in fact 1. So try this example here. Find a vector u in the direction of the vector 6, -1, and verify that the magnitude is 1. All right, if you tried this out, you should have gotten 6 root 37 over 37 and negative root 37 over 37. Then it does verify to be 1. The unit vectors 1, 0, and 0, 1 are the standard unit vectors are denoted by I equals 1, 0, I equals 1, 0, and j equals 0, 1, as shown in figure 618. Note that because lowercase letter I is in boldface and not italicized, it's used so that it's distinguished from the imaginary unit I, which we've learned previously. So these vectors can be used to represent any vector v, the I and the j, because v, the vector v, v1, v2, is v1 times 1, 0 plus v2, 0, 1, and we just rewrite it as v1i plus v2j. The scalars v1 and v2 are the horizontal and vertical components of v. So v1 is the horizontal, and then v2 is the vertical components of v. So just think about the horizontals are x's, the vertical component is our y's. The vector sum vi plus vj is a linear combination. So we're going to do linear combinations of the vectors I and j. Any vector in the plane can be written as a linear combination of the standard unit vectors I and j. So what I want you to see from all of this is that I is just the horizontal component. It's where we move right or left, right if it's positive, left if it's negative, and then the j is where we move up or down, up if it's positive, down if it's negative. So let's try this example. Write a linear combination of unit vectors, and then what we want to do is we're going to go ahead and graph it just so you can kind of see what this means. Let u be the vector with initial point 2, -5, and terminal point -1, 3. Write u is a linear combination of the standard unit vectors I and j. Now the terminal point is important because we will be subtracting. So to find this, you're going to do u equals, and then the x, so we're going to subtract the x's and subtract the y's, so -1, the terminal point first, -2, and then we're going to take the y's, 3 minus a -5, and so this is going to be -3, and 3 plus 5 is 8. Now we're going to write it as a linear combination of unit vectors, and so all that is you write it as -3i plus 8j, and we are done. Now what we're going to do is I want to graph it, so let me graph this here. So it gave us an initial point and a terminal point. So the initial point is 2, -5, so write 2 down 5. And then the terminal point is -1, 3. So left 1, up 3. So that's the terminal point of this vector. Okay, so sorry, I can't draw a straight line there. And then what I want you to see is how it relates to -3i and 8j. So what I said with the I, that means that's where we go right or left. That's a horizontal. So notice I go 1, 2, 3. So I go 3 left, and then I am going to go 8 up. 1, 2, 3, 4, 5, 6, 7, 8, and that's my 8j here. Okay, because in the homework it may ask you to graph, and just want to make sure you can do that. Now try this example. Let u be the vector with initial point -2, 6 and the terminal point -8, 3. Right, u is a linear combination of the standard unit vectors I and j. Okay, if you tried this out, you should have got -6i minus 3j, and then I drew it. So I put the initial point here, which is -2, 6. The terminal point is left 8, up 3. Then I just tested it. So from this initial point, I went left 6, -6, and down 3.